Hi, welcome to Neuroverse
a podcast hosted by Carolina
and Clara, where we discuss all matters from neuroscience to philosophy and beyond.
In today's episode, we have a special guest, Liza Rozenberg, and she will be introducing today's topic. She's doing a degree in physics in Princeton University.
Hello. So today I'm going to be talking about understanding the world using physics, which is a very, very broad topic, and there are a lot of different areas of physics that can be used for understanding the world. But I think I'm probably going to talk about more kind of edge cases where our limits of understanding are actually tested. Like, for example, in quantum mechanics and understanding the universe is like a concept, etc.
Yeah, that sounds really cool.
Sounds fascinating.
Yeah.
And slightly different to what we usually discuss.
Mm-hmm.
Yeah.
Neither of us are experts in quantum mechanics or
not at all
quantum gravity, so please enlighten us.
Well, actually, I think although nowadays science as we study it is very divided between like physics, neuroscience, they're in fact, I think, very intricately connected, because whenever we study the world, we study it through our senses and we study it subjectively, nevertheless. For example, there's some famous quote, I think, by Heisenberg, who's like one of the inventors of quantum mechanics. And he said something like, what we observe is not nature itself, but nature exposed to our method of questioning, which sort of makes it very clear that whenever we probe the world for certain properties that we're looking for, we are imposing on it certain expectations. And I don't think we can ever get a full objective picture by studying it using our own minds. And not to even mention the fact that some scientists think that consciousness and just the functioning of the brain in general definitely has to have quantum mechanics in order to actually work. I don't think it's been proven. There are some kind of more niche theories about this, I think, for example, by Penrose. But it's generally accepted that probably there are things in neuroscience that need some very sophisticated physics to understand how the brain works and how we actually understand and interact with the world. Like I remember in philosophy class, we were discussing how color is not actually there. Like it's just something we perceive because of the way that photons interact with objects and how they interact with the surfaces of the objects, and like whether it's jagged or smooth, it makes it either like silver or dark maybe. I think it's very fascinating that we see a world only in one sort of manifestation, but it's actually it's something deeper and something we don't necessarily have direct access to.
It's so interesting that that's the first thing you started the discussion off with as a physicist, because physics and mathematics are the more objective of the sciences compared to like biology or even chemistry, in my opinion.
And like you mentioned, as humans, we are limited through our own faculty, and that like everything will be inherently subjective, either due to our previous memories and context, as well as, like we discussed in our previous episode, noise in the brain and how it causes us to basically input the same information in slightly different ways. And with physics and maths, it seems to be a lot more quantifiable, and like that's the equation. Like there's no ambiguity.
Yeah, that's interesting, because I think there seem to be two sort of broad camps in physics. Like one is kind of the shut up and calculate approach, where you just kind of take the theory, use its predictions, and just like compute stuff and get results, and the results match what you detect in experimental data, and you're happy. But the other approach is to actually think about what it is that these calculations are telling you. Like even in quantum mechanics, it's notoriously extremely good at matching our experimental data. But at the same time, I don't think anybody agrees on what exactly quantum mechanics means, because essentially some of the postulates of quantum mechanics are such that when you compute, every outcome has a wave function, which kind of codes how likely it is that you're going to measure a certain value. And there's a range of values that could possibly be measured that are accessible in some measurement. And this wave function tells you which are possible, but it doesn't necessarily tell you which one is going to be detected for sure. It can, but I mean, that's only after you make the measurement. But once you make the measurement, you get some value. So then you kind of know what the state of that system is at that point. But how exactly it got from being like in an uncertain state to being in a certain state, we don't know. Like, we don't know what exactly occurs. Somehow it just kind of collapses. We call it the wave function collapse. How it goes from being just probabilities to like a certainty. We hope that there might be some physical principle that tells us how it undergoes that jump, but nobody knows what that principle is. And it's some people are just happy with accepting it as it is, and because it works very well, sure. But if we actually want to make progress in more deeply understanding science and the world, we need to pause and think about what it means. And I mean, there are like so many different hypotheses about or like interpretations. They're called interpretations of quantum mechanics, like what these things mean. Like, for example, one hypothesis is that, oh, this wave function, upon measuring the system, the world kind of splits into multiple branches. It's like the many worlds interpretation of quantum mechanics. So they all exist at the same time, and it's just you happen to be in one of the branches, and the others also exist, but like they're just inaccessible by you. Like, we have no proof.
This is really ignorant of me. Is that like Schrodinger's cat? Like, Schrodinger's cat is there, but also not there simultaneously?
Yeah, so Schrodinger's cat is, I suppose, maybe the most famous thought experiment to see what the problem actually is. To quickly recap what the setup is. So you have a cat, and the cat is stuck in some box, and with the cat there's also some radioactive substance that is poisonous, and we assume that like just one emitted radioactive particle from this substance is enough to kill the cat. And we have this closed box, we don't see what happens, and this radioactive substance might decay at some point and might not. So radioactive decay is random, so it can occur like at any point basically. We don't see what's inside, so like we don't know if it's alive or not. So if we were asked like what is the state of this system, in order to give the full picture, we would have to write down a wave function, a description that involves both the cat being alive and the cat being dead, because the particle could have been emitted and also could not have been emitted. And so, like, colloquially speaking, yeah, the cat is like both dead or alive. But once you actually open the box, you see whether the cat is dead or alive. So it's kind of like decided. So the uncertainty collapses into something that we know for sure. And according to the many worlds interpretation, upon opening the box, the world sort of like splits into two branches. So one of the branches is the one with the cat being alive, and the other one is with the cat being dead. If you observe the cat as being alive, it just so happens that you're on the branch that has the cat being alive. But there's another you perhaps that detects the cat as being dead, and that's the other branch that you don't have access to. And I mean, like, this raises so many questions, and probably for you as well, because like, oh, like, so there's two copies of you? Are you both conscious? Like, if you're like exactly the same, then why do you not like have some sort of mind communication with yourself in the other branch? Like, what's happening? So yeah, so it's very confusing. And also there's no like experimental proof, or even, it's not even, I don't think, at the moment falsifiable. Like, we can't prove it either way, because if the other branch is not accessible, how could you ever test that it actually exists?
That's so interesting.
Yeah. It's interesting you mentioned that thing about the system. So in this case, we would be outside of the system, right? And trying to understand what's happening within it. Before this episode, I remember you asked the question of whether or not we can study something from inside it, so from inside the system. And I guess that's kind of like what we do as humans and as neuroscientists. You know, we have a brain and we're trying to study like our own brain, as well as physicists who are trying to study the universe whilst being within it. So what is your opinion on that, and like the limitations of having of trying to study the system from within the center of it?
Yeah.
Are we the center of it? That's such a human thing to say.
Okay, fine.
But still, yeah.
But I think even being part of the system still kind of makes you interfere with it. And it somehow changes the results you get. But like, if you weren't there, who would even be observing the results? It's like, yeah, I think to me, it's clear that like the fact that you're existing within the system has to somehow factor into the theories that we write down to describe the world. I don't know.
Do you think there's also a lot of bias, and like our own interpretation of the data may mean that the system is actually different to what we believe it is?
Yeah, I think there's definitely some bias just due to human senses. And I think we're doing our best to kind of create experimental setups that kind of exclude human interference as much as possible. But I think it's just always there. Like in quantum mechanics, there's always that measurement problem. Like it's the process of measuring something is like actually not very well understood at all, like what exactly happens to the system as soon as you measure it. And yeah, with relation
Can you give an example of that?
I think just in general, even the thing that I was talking about before, like when the wave function collapses, that's sort of like at the point of measurement, it collapses.
Okay.
So like it goes into a decisive state. But how exactly it overcomes that jump is unclear. And so that's kind of the measurement problem. Because to measure something, you have to like look at it, or I don't know, touch it, or measure it with some apparatus. But like, I guess you have to interpret it. You have to look at it for it to be looked at. I don't know. Yeah. And even like with the entire universe, even when we study like some subset of the universe, the rest of the universe is still there, and like it still interacts with the subset that you're studying. So I guess it's always like you have to make sure that the fact that there's an outside universe outside of this small system that you're studying, that it's sort of self-contained, that it makes sense to like ignore the fact that the rest of the universe kind of exists around it. But that's not always a good idea, because like, for example, if you had some, I don't know, a cube of ice in some really hot water, and you were just like focusing on the ice and it was melting, and that would be a system that's like gaining energy from the outside, gaining some heat, you would need to take into account the fact that it's like in some bowl of water or something. But if you're just ignoring that, it doesn't give you the full description. And whenever you're studying subsystem, you have to make sure that whatever you're like excluding from the picture is not that important to your description, because otherwise then you won't be capturing the essential features. Yeah. And with the brain as well, I think a lot of the time we take for granted that whatever our brain tells us is true, when in fact, most of the time it's not. It's very, very easy to fool humans. I think we don't give our brain enough credit about like how powerful of a deceiver it can be. And I remember reading about some sorts of experiments that were done where like a person was put in a certain brain state, and they were kind of forced into feeling like there's a ghost behind them or something like that. Like there was no ghost. They were in a lab. And I think, yeah, there's like a lot of stuff that can happen to your brain that you're not necessarily aware of. I mean, there might be some natural processes that happen, like maybe some radiation or something that you don't see because we're only restricted to seeing the visible light. Yeah. I guess you guys can probably talk about that more, since you're more closely acquainted with neuroscience.
Well, it just really reminded me of what we've mentioned in many other episodes of the conscious experience has been just described as a living hallucination, because essentially everything we experience is in a way a hallucination, because it's a combination of both what we're taking in physically from the world, such as you described with color, like the bouncing of
The
photons and light and photon absorption and emission, as well as the top-down processes and the integration of our memories, and all of those processes shape everything that we take in.
Yeah.
Yeah.
What you mentioned about the scientific experiment, yeah, there are several studies about illusions and trying to assess like touch and that kind of thing, as well as
phantom limb
syndrome. Yeah, which is where a person that has an amputated limb still feels pain in that area. So yeah, it's just another example of the way that, I don't know, the brain is incredibly complex. And it's also another thing you mentioned about trying to study a specific element of the system and ignoring the rest of the system. Like, it doesn't quite work like that. In neuroscience, I feel like we can be a bit guilty of trying to do that when we record like a single neuron or
and then generalizing it to the whole brain. Yeah. Well, I often question, this was something else we discussed in the noise episode, and it's about how humans are pattern seekers, and we look for patterns in everything. And I always question, like, you know, even with the most generalizable theories or equations, what if they're really just made up? Because their purpose ultimately is just to help us understand the world. It doesn't necessarily influence the world. Although, as I was saying that, I realized that it totally can, because we can make inventions that influence the world.
Yeah. But I guess, you know, regardless of whether or not we understand it, and regardless of the way we write it down as an equation, like the physical laws will remain the same.
Yeah, but what if they don't? What if their existence is only for the purpose of human interpretation?
Yeah, I think this plays a little bit into that thing of like, you know, does a tree make a sound when it falls if no one's there to hear it?
Yeah, I think there's a lot to be said about how fundamental our science actually is. Like, the descriptions that we have, how fundamental are they, and how closely do they actually describe the fundamental reality? And it's that question of like, oh, is math invented or discovered? You know, perhaps it's just a language, and maybe it's very good at telling us how the world behaves. But my guess would be it's probably not exactly the way the world is. Like, it's a language. It's like, I don't know, speaking Spanish or English to describe the same thing. Like, you're still describing the same thing, but that thing is not exactly the Spanish or the English itself. Like, those are just the languages that are used to describe it. And perhaps it's something like that. And I think since math forms the foundation of a lot of science, and sort of helps it be grounded in objectivity, I think it's all gonna, like, all the science that we do is bound to have some human imprint on it. And because we have to visualize all of these things, and I don't doubt that there are things that we just cannot conceptually visualize, and perhaps there are things that we just cannot understand, which is super, super frustrating to me. But perhaps that's the case. Like, maybe there's just certain, like, for example, there's languages that don't have words for certain concepts. Perhaps we just don't have words in our mathematical toolbox to describe some things that currently lie outside of our understanding. And I'm not quite sure how to expand our vocabulary. I don't know.
Yeah.
But I think one clue for the fact that this might actually be the case, that like there's some limitation to exploration by virtue of just us humans not really being able to imagine certain things conceptually, is that there's a lot of new mathematical theories that actually stem from physics. That, like, in physics you study something and then you kind of start seeing some patterns or some certain behaviors that you think maybe there's some underlying reason for them, and then this can lead to some mathematical theories. And it's happened many, many times, especially like during the creation of string theory or some other like more technical aspects of theoretical physics. There were new mathematical theories that arised from that. And it's sort of like the tools come from the fact that you're needing to solve some problem. And it's like, I guess sometimes we can't assume that, oh, we've discovered all the tools we could ever need to describe the world. Like there might be more. And maybe like that's the way we'll discover them, is by stumbling upon a problem and then seeing how exactly we can solve it and then developing tools to solve it. Yeah, but I think there's probably some things that we just cannot understand, although I sincerely hope that's not the case. But I don't know, or maybe we can somehow expand to the abilities of our brain. I'm not sure. I don't know. Or maybe is it limited by our biological makeup? I'm not sure.
Well, first I have to say, I think that was so well said.
Yeah.
And I wanted to respond to the fact that as you touched on, what we know and what we know mathematically and in terms of physics is really based on what we need to know as well. And so maybe that's the limit, like we are the limits of ourselves.
Like we're looking in the wrong areas, perhaps.
Well, we're looking in the areas we want to.
Yeah.
Which then is not so limiting.
I also think related to that reminds me a bit about machine learning and just inputting like huge amounts of data and then it churning out some analysis or conclusion of the data. And the way that we process data, the way that we analyze data ultimately then influences our interpretation and our perspective of the world. You know, an easy example with that is in neuroscience, we can measure electrical activity of the neurons using either tetrodes or neuropixels, and that gives us, what is it, thousands, millions of responses of spikes. And then there are these algorithms that have to sort these spikes. And these algorithms, the algorithm you choose is very arbitrary. But of course, the way that you filter out the noisy data is going to ultimately determine the conclusion that you derive. So in this sense, the way that we go about analyzing the raw data that we have from the natural world, I think determines then our perspective of it.
Yeah, because we're ultimately looking for a pattern. Sorry to repeat myself, but depending on what analytical method we use, we can find different patterns sometimes. Yeah.
In touching what you said about whether or not we can perhaps expand the mental capacities or whether we're restricted in our biology, this ties into one of my favorite topics, which is enzyme-directed evolution. I feel like I bring this up in almost every episode, but this is relevant. So enzyme-directed evolution is where you basically modify an enzyme through several series of like evolution and basically direct it to do the thing you want it to do. And in this way, there have been experiments where carbon has been able to bind to boron and silicon, which used to be unheard of. And now they're thinking that potentially we can expand the genetic code by introducing these non-organic elements. And by expanding this genetic code, we can expand perhaps our biological capabilities to what you were saying.
Oh my gosh, this actually reminds me of something. So related back to what you were saying earlier about AI and machine learning, potentially expanding maybe what we can find out from the data we collect, from the experiments we do. And then enzyme-directed evolution also reminded me of just evolution in general, about how the process of evolution is to create or to utilize variation and variability and then find the best solution from that. And from what I read about machine learning and the way that that is being evolved, it's through expanding how many different types of patterns the machine can find in the data. And this makes it better, more capable of solving problems, more so than humans, and more reliable. And so that, I feel like the basis for this all is to expand our horizons of what we can know.
That's interesting. Yeah, machine learning is like something I think pretty mysterious even to the people who study it because nobody really knows how it works exactly and why it's just so good at being so effective.
You mentioned potentially expanding the mathematical toolbox. Do you know how you could ever go about that? Like, do you have any ideas? I have no idea. I'm very much out of my depth of comfort.
No, I mean, I think it's hard to say exactly how it's going to be done next, but I know that for instance, there were some physical theories that needed some descriptions in terms of, for instance, like certain geometric shapes in math, and there wasn't much known about those geometric shapes because they were like in multiple dimensions, more than three. So people really can't visualize that. So it's literally just, you just have to bash it with math, and maybe use some intuitions about like three-dimensional space. But I think because like there was something needed in physics, then sort of the mathematicians were led to study those objects that might be useful, and through studying them and kind of like investigating their properties and maybe like using some intuition, they found some theorems. I guess like math is built on mostly theorems and proofs, and that's what makes it so rigorous and rigid. I think a lot of math can be built up from some unexpected hypotheses, and then people spend years and years trying to prove or disprove them. And then if they're proven, then we can use them to build some new stuff, et cetera, et cetera. Yeah, it's kind of like a long process, but still at the end, at least you obtain something that's definitely true, as long as it's like, I guess on the foundation, it's like the mathematical axioms, and then you keep building, and you know that each of the levels is true because you've proved it. So that's very comforting to me. But yeah.
Going back to our conversation on systems, I found this interesting paper that wanted to compare the morphology of neurons with the morphology or the structure of space. So this is about, it's called the quantitative comparison between the neuronal network and the cosmic web. And it's actually some really interesting comparisons. I just want to show you some images, which we'll put later on our website so everyone can take a look.
Interesting.
Can you spot the differences? Aren't these really similar?
For sure, they are, yeah.
So what we're looking at right now is some images of either the cerebellum or the cortex, as well as cosmic web,
But what is the cosmic web?
Well, they call it dark matter, I believe.
I think it's most likely like the cosmic matter, that's how it's like distributed in empty space, right? Well, empty space.
Yeah.
Of the universe.
Do they quantify the similarities?
So yeah, they do. They compare basically, so the brain is composed by water, and it contains around 70% of water, 10% of lipids, 8% of proteins, 1% of carbohydrates, etc., etc. And in comparison, the universe is apparently made up of 73% dark energy, 22% of dark matter, 4.4% of ordinary baryonic matter, etc., etc. So the ratio between these substances are similar, and as well as, so in terms of quantifying like how much memory the brain can process versus how much like also like information, let's say the universe can process. These are, I'm really not an expert. I'm just using these terms, but I'm just copying the terms they used in the paper. And basically, so the way they looked at it in terms of the neuronal network is they were looking at like dendrites and the number of nodes in the neural network, and how that yields 2 times 10 to the 16 bits, which is around 2.5 petabytes in terms of memory capacity. Whereas for the cosmic web, it says that it's around, they use statistical complexity, and that it's around 3.5 times 10 to the 16, which is around 4.3 petabytes of memory, which is also really similar in terms of like quote unquote memory storage or information storage. And so I just think it's a really cool comparison. And if we do look at neurons, sometimes they do kind of look like stars, right? Like some of the morphology of the neurons, where the way that they spread out and stuff. And so I just think it's a really cool comparison. Or glia, exactly.
The other cells in the brain, yeah.
That's cool, yeah.
Yeah.
I mean, I think maybe it could be because certain shapes, certain arrangements are more favorable, energetically speaking, or like just according to some laws of physics. Perhaps, maybe it's like in the same way that, like, I don't know, a rope when it's just like hanging, hangs in a specified shape that you can compute what that shape is, and it's like kind of looks like a parabola, but it's actually not. It's called a catenoid, I think. Yeah, maybe there's just some physical reason why a certain shape or a certain arrangement is favorable.
Probably.
Talk about structure function relations. Maybe if it needs to serve a similar or comparable function, then it tends towards a similar structure.
Potentially.
It's really hard to like go from something really specific to something really general, and I think we always have to be really careful with like from studying our examples that we know so well, like we think we understand, and then move on to generalizing those conclusions to the entire world. It's very dangerous to feel overly confident.
So on that note, I think we're gonna finish today's episode, and thank you so much for joining us, Lisa.
Thank you for having me. It was super fun.
Such a pleasure talking to you.
Yeah.